Hello, I'm James Floyd, ready to do the last problem of our problem set from chapter 30. And this problem is in module 8. So let's just take a quick look at module 8. Module 8, energy density of a magnetic field. And our learning objectives identify that energy is associated with any magnetic field. And over here, apply the relationship between energy density UB of a magnetic field and the magnetic field magnitude B. Some of the key ideas, well, if B is the magnitude of a magnetic field at any point in an inductor or anywhere else, the density of stored magnetic energy at that point is, and we have this little formula and we are going to use it, UB equals B squared over 2 epsilon naught. Problem 70, chapter 30. Okay, the figure 67A shows in cross section two wires that are straight, parallel, and very long. These two wires here. The ratio I1 to I2 of the current carried by wire 1 to that carried by wire 2 is 1/3. Wire 1 is fixed in place. Wire 2 can be moved along the positive side of the x-axis so as to change the magnetic energy density UB set up by the two currents at the point. This one can be slide, and this is slides to infinity. UB approaches this value. Figure 36.7b gives UB as a function of the positive x of wire 2. The curve has an asymptote of UB equal 1.96 nanojoules per meter cubed as x goes to infinity, and the horizontal axis scale is set xs equals 60 centimeters. That's this scale here. What is the value of A, I1, and B, I2? Now, we notice at this point, which is 2 centimeters, that this wire and this wire will be 0. So this is the way we're going to start setting up this problem. So we have mu sub naught I1 over 2 pi d. This is just your formula for a very long wire. It's going to equal mu sub naught I2 over 2 pi times 0.20 meters. And we get this 2 meters right here. This is 20 centimeters. This is where the two wires cancel each other and the results equal 0. This is why we can set each formula of I1, I2 this way. Now we also know that I1 is 1/3, according to the problem, of the current carried in I2. So we can substitute 1/3 I2, which is be equivalent to the current in this expression here. So we have mu sub naught I2 over 2 pi d, and that's 1/3, will come here, will equal to mu sub naught I2 over 2 pi 0.20 meters. Now at this point we can solve for D, so let's just take this denominator and set it out and solve for D. So we have 2 pi D3 is equal to 2 pi times 0.20 meters. The pi's will cancel out, and D is going to equal 0.20 meters divided by 3, which is going to be approximately 0.07 meters. Now we're going to use the fact that UB equals B squared over 2 mu sub naught. So if we solve that, that would be B squared equals 2 times mu sub naught times UB. Now that's the energy density, and B, this will go to B equals the square root of 2 mu sub naught mu B. Okay, what we can do now is that we can set this quantity to this quantity. And we'll do that. We'll have mu sub naught I1 2 pi D is equal to the square root of 2 mu sub naught mu B. When we do the math here, dividing this into this, 2.86 times 10 to the minus 6 I1, that's when we divide mu sub naught into 2 pi D, just simplifying it, is equal to, and when we do all the math in this and take the square root, we're going to get that this expression equals 7.0 times 10 to the minus 8. So when we divide, we have I1 equals 7.0 times 10 to the minus 8 divided by 2.86 times 10 to the minus 6, and that will come out to be 24, I've done the calculations a little earlier, milliamps. So that's the value we get from I1. And we know I2 is 3 times I1. So I2 is going to be 3 I1, which is going to be 72 milliamps. So that's the answer to A and B of this problem. Thank you.